you for joining me for this Zemax webinar. Today we're going to talk about the brand new OpticStudio 16.5 beta program. My name is Kristen Norton and I'll be your host for today. In this webinar, we are going to start by talking about the OpticStudio beta program. Then we'll talk about who is eligible to sign up for the beta program. Next, we'll talk about how you can sign up for the 16.5 beta program. We will also want you to send us your feedback and your questions about the new features, and I'll show you how. After that, we'll give you a sneak peek of some of the new features which will be coming out in the 16.5 release. OpticStudio betas are pre-release versions of the software. We want to get your feedback on the new features that we have planned for the next release. Joining our beta program means that you get to take part in shaping the future of OpticStudio. You'll be test driving beta versions and sending us your feedback as well as your questions. All of this means that you can help us make the OpticStudio 16.5 release our best one yet. So, who can join the beta program? Anyone with current support can join the OpticStudio 16.5 beta program. To sign up for this new 16.5 beta program, all you need to do is go to the website shown here on the screen. You will just be asked for your name and your email address, and then you'll receive an email with a link to download the latest 16.5 beta. Once you start test driving the latest OpticStudio 16.5 beta, we'll want you to post your feedback and any questions that you may have in the beta release section of the Zemax forum. You can see the link to get to the Zemax forum here on the screen. Each new feature in this beta version has its own child forum. That's where we'll want you to post your feature-specific questions. Then, the OpticStudio support and product management teams will be responding to your posts. Note that you can also get to our forum from our website. Just go to zemax.com, click on OpticStudio, then go up to the Resources section of the main menu, and you'll find the forum link under Community. Now we're going to talk about some of the new features in the 16.5 beta, which are planned for the 16.5 release. Dr. Sanjay Gangadhara will be helping me today, and he is our Director of Development. Together, we're going to show you how to use some of the new features in the 16.5 beta. Up first is the new Non-Sequential Geometric MTF calculation and some new filter strings that you can use in layouts as well as in array database files.
Hi, welcome to the webinar today. Let me start by saying that a number of great new features have been added to OpticStudio 16.5. One of these is the calculation of the geometric MTF in non-sequential mode. This MTF calculation can be accessed on any detector rectangle object in a non-sequential system. Just shows up as one of the drop-down options under the Show As input to the detector viewer. MTF is generally used as a specification for the design of high-quality imaging systems, and such systems are generally created in the sequential mode of OpticStudio. However, once you are interested in analyzing the effects of stray light in the system, resulting from either intended or unintended sources of light, the system needs to be moved to non-sequential mode. This can be done easily in OpticStudio using the Convert to NSC tool. Let's start, for example, with the double Gauss 28-degree field sample file provided in the OpticStudio installation. To prepare this system for non-sequential export, we can first use the Design Lockdown tool. This tool was introduced with OpticStudio 16. I'll go ahead and save the lockdown file to a new file name so as to not overwrite the existing file that's already here. The resulting lockdown file can then be converted to non-sequential mode using the Convert to NSC tool. Beginning with OpticStudio 16, this tool allows users to include both sources and detectors in the converted file, allowing direct comparisons to be made between the sequential and non-sequential results for the initially converted system. Once the file has been converted, we can run a ray trace to generate results on all of the detectors in the system, with each detector representing the image that would be formed by each of the field points that were carried over from the original sequential system. Once the ray trace completes, we can then look at the MTF for each detector rectangle in the system. And I'll go ahead and clone these windows so that they're set up to look at MTF, and I'll just go ahead there and switch then between the different field points to be able to look at the MTF at each field point. You can compare the results for each field point in the non-sequential model with the corresponding results from the original sequential system, and you will find excellent agreement. The advantage now of working in non-sequential mode is that we can look at how the MTF on each detector is modified by either accounting for sources with finite size, which we don't have available in sequential mode, or by accounting for unexpected light reaching the detector. The latter could be the result of light coming from other field points that reaches a given detector due to splitting or scattering, or could be light from other unintended light sources altogether. For example, stray light coming from outside the field of view of the system. Just for this example, let's consider the effect of scattering and how scattered light from other field points in the system can land on the on-axis detector. To do so, let's just go ahead and simplify our design. We'll go ahead and remove the detector color object from the system, which isn't being used by the MTF calculation. And we'll go ahead and increase the size of each of our field detectors to be large enough to capture some of the scattered light that will be introduced into the system by applying scattering in the system. Before we do any scattering in our system, before we apply a scattering profile in the system, let's go ahead and now ray trace with the larger size of the detector. This is important because the larger detector, given the same number of pixels on each detector, will change the detector resolution, and this will in fact affect the MTF results that are seen on each of the detectors. So again, here's our results now for the geometric MTF on our on-axis detector, which is the detector we'll focus on for our later studies. But then here are now our MTF results from our off-axis detectors as well at the lower detector resolution, the larger detector size. Let's go ahead now and add just a bit of scattering to the system, just again as an example. So I'll go ahead and add Gaussian scattering to the front face of the first lens in this double Gauss system. So for the front face there, I'll go ahead and make this a Gaussian scatterer. I'll set the width of the Gaussian distribution to 0.1, and I'll set the scatter fraction to 1 so that all rays which hit this surface will undergo scattering. We can go ahead and rerun a ray trace, but again, before we do so, since we're focusing on the on-axis field just for this example, I'll go ahead and clone another window that shows that on-axis field, and then I will go ahead and lock the original window so that I can have the results of the original window there for comparison. And then I can go ahead and run a ray trace with scattering now turned on, and go ahead and see how the MTF is affected. And you'll see, not surprisingly, that the MTF is significantly affected by the presence of scattering in the system. So the MTF now drops off dramatically as the result of scattering. Now this, of course, could just be scattering of the light that would have reached the detector from the on-axis field to begin with. But some of this might actually be the result of light coming from off-axis fields that now scatters into or onto the on-axis detector. And it would be good to be able to determine how much of the light that's hitting this detector is coming from off-axis field points that are scattering onto the detector. So to look at that result, we can conduct that investigation by saving the ray trace results to a ray database file. And so then the ray database file, this will take a little bit longer as we're saving the results to the file, but the file will then allow us to do some queries of the rays that are actually landing on this on-axis detector. Okay, so now we're done after about half a minute. Um, and so now in order to say, okay, well, how much light is falling on the detector from off-axis field points? So you can see right now from all of the field points, the total number of hits reaching this detector is about 6,000, corresponding to about 6 milliwatts of power. We'll go ahead and load the, and I'll go ahead and just look at the irradiance for this comparison. But I'll go ahead and now load the ray database onto the detector. So now we're going to be reading data directly from that file that was saved. And now I can filter those results. I'm going to be looking now for light that is coming specifically from objects 2 and objects 3 as sources. So those are the off-axis field points, and I'm going to look and identify how much light is coming from those field points. So go ahead and hit OK. So I'll take some time to update as it's reading through that database. And you can see then that that result then shows about 20% or so of the light that's landing on this on-axis detector, about 1.2 milliwatts of the 6 milliwatts originally, are coming from these off-axis field points. What would be helpful now is to be able to identify the paths that the light took from those off-axis field points to get here. How did the light, that came from an off-axis field point scatter onto this on-axis detector? Now we could do that by loading the ray database directly onto a layout plot and then investigate the rays directly in the layouts. So I'll go ahead and do that. And so you can go ahead and first, again, load. I'm not going to auto apply here because I want to go ahead and set the filter string first. So I'll go ahead and load that ZRD. And in this case, I'm going to go ahead and set the same filter. So we're looking at light from object 2 or object 3 as the source. We also want to make sure it's light that hits our on-axis detector, which is object 12. So we're going to look for light that hit object 12. And you can go ahead and hit OK. And you can see not surprisingly, that because there's over 1,200 hits on the detector, that we're going to end up seeing a large number of ray paths populated in this layout once we're finally able to visualize them all. And so again, you can see a ton of rays here that are actually being launched from each of the sources that make it onto the detector as the result of scattering through this first surface. It might be useful to be able to identify a smaller subset of rays so that you don't necessarily have to look at all of the rays that meet that condition, but you only want to look at some handful of rays. With OpticStudio 16.5, we've also introduced a new filter string into the software that allows you to do just that. So then rather than looking at all of the rays that meet the filter condition within this ray database file, you can actually select some number of rays. And the syntax for doing so is shown here. So it'll curly brackets and then the number sign. And then you select how many rays you want to see. So in this case, I'm going to say that I want to look at the first 50 rays that meet the filter string condition from the ray database file. And then I'll go ahead and add an extra set of parentheses here so that I can have the proper syntax in place. So basically you have a syntax that shows curly brackets number and how many ever rays, n number of rays that you want to see out of the ZRD that meet this filter string condition. And then in parentheses, you then specify again the filter string. And then now by applying this, you can see now we've reduced significantly the number of rays that are shown in the layout plot. And again, that happened much faster. We were able to render and visualize that much faster. And so you can play around with this number, again, just to get a sense of how many rays you indeed want to be able to see from each of these sources that meet a particular filter condition. Now, the syntax not only allows you to select the first n number of rays from the ZRD, which is being done here, but if we wanted, we can select any subset range of rays from the ray database file as well. And in order to do that, like let's say rather than wanting to see the first 20 rays out of the ray database file, which is what I'm doing here, I wanted to see rays 100 through 120 out of the ray database file that meet this condition. So the syntax there is simply to use the first number, what ray number you want to start with, dash the ending number. So in this case, 100-120 will then select rays 100 through 120 out of this ZRD that then also meet this condition. And then so I can then start to see different rays out of the ray database file that actually meet the filter string of interest. Now this new syntax, this new filter string, I should say, can be applied in the layouts when the layouts have a ZRD on them. It can also be applied on ray database files that are used in any of the ray trace analyses, such as in the path analysis. So in general, the path analysis will look at all of the rays that are stored in the ZRD. So for this case, that ends up being 3 million rays. But again, I can use the same type of filter string to be able to say that I only want to look at, say, the first 100 rays in this ray database file that meet, again, I'll just choose the same filter condition, rays that come from the off-axis field points, but also hit my on-axis detector. And I can go ahead and then see paths, basically, that each of those rays take. So here is the path that rays from source number 2 take. Here's the path that rays from source number 3 take, leading up to the 100 rays that I had asked to be evaluated using that filter string syntax. The filter string can also be used in the layout plots itself without needing to use a ZRD. However, in general, in order to have some effect, we would need to increase the number of rays that are being shown by the layout. So in this case, we only have 10 layout rays from each field point. So if you increase that to a much larger number, let's say 1,000 rays for each source, then we can actually filter rather than having to see all 1,000 of those rays. You can again filter and say that you only want to look at, say, the first 10 rays out of those that again meet any given particular filter string. And you can see in this case, actually, for the 1,000 rays that we've selected, there aren't any that meet that particular string within the random set of rays that we've selected. We could certainly change the syntax just to illustrate the benefit. But again, here now I'm just looking at 10 rays from either object 2 or object 3 that meet, again, the first 10 rays that meet this filter string. So there are just 10 rays from object number 2 in this case. But again, this can then be combined with any type of a filter syntax in order to generate a complex filter string, but that allows you to then only see or selectively see a few rays that meet any particular filter string syntax.
Next, we're going to talk about the new Flux versus Wavelength support for photometric output. The OpticStudio 16.5 release will have a new capability built into the Flux versus Wavelength analysis. And this new feature was added in response to requests from customers who were working with photometric units. The Flux versus Wavelength analysis in non-sequential mode, you can see this here in the Analyze tab. This will now support a photometric output in lumens as well as a radiometric output in watts. The choice of units will be tied to the source units as they are currently defined in your System Explorer. To demonstrate, I have a sample file open now of a white LED which uses a blue Osram LED and a phosphorescent material to emit a white spectrum. And you can see the white spectrum here on the detector color in the shaded model. Now if you look over in the System Explorer on the left-hand side, in the Units section, we can see that my source units are in lumens. Therefore, my flux versus wavelength analysis should report the flux in lumens as well. To show this, let me run a ray trace. We'll save the rays, and then I will open up this ray database file in the new flux versus wavelength analysis. Now that the ray trace is complete, I'll click the Exit button and open up the flux versus wavelength analysis. Expand the settings The correct ray database file has been selected, so I just need to change the object to the detector color. I also will increase the maximum wavelength here so that we can see the larger spectrum which comes from the white phosphorescent emission. And now we can see the flux in lumens versus the wavelength. Up next is the enhanced phosphors and fluorescence model. The 16.5 release of OpticStudio also includes some new enhancements to the photoluminescence model, which was requested by multiple customers who've been using this photoluminescent capability and who wanted it to support a wider range of applications. Now, before I jump into the changes, let me review how our photoluminescence model has functioned in past releases. This here is a sample file of a white LED, which uses a blue osram LED and a phosphorescent material to emit a white spectrum. Here in the shaded model, you can see the white spectrum on the detector color. In the non-sequential component editor, we can click on here Object 3 and expand the object properties. Then in the volume physics settings, we can see the phosphors and fluorescence inputs. Photoluminescence is the tendency of optically active molecules to absorb, downconvert, and re-emit light. This is associated with a scattering event, which we described using the me-scattering DLL. Then we use separate spectrum files to account for the absorption, emission, and excitation of the photoluminescent material. The absorption spectrum is the probability that a photon of a certain wavelength will be absorbed by a molecule. The emission spectrum is then used to calculate the intensity spectrum of the photoluminescent emission, and you need either an excitation spectrum or a quantum yield spectrum to define the wavelength-dependent efficiency factor for the down conversion process. In the previous photoluminescence models, the me-scatter model, shown here, okay, this was used to calculate the probability that a ray would undergo a scattering event and undergo a photoluminescent interaction. This would be problematic in some scenarios where, for example, a fluorescent dye is contained within a non-scattering material. With the previous model, even rays that were not downshifted would still be scattered, and this would not actually be the case in a non-scattering medium. To accommodate for these scenarios, we've modified the phosphors and fluorescence model, or photoluminescence model, so that there are two different mean-free path inputs. There's one for the photoluminescence settings here, and then another one for the me-scattering settings shown here. We also added a radio button to toggle between the mean free path and the particle density, which is used for the me-scattering distribution. In addition, you can actually revert back to the previous model using the radio button here. Basic is the old version, and standard is the version which includes the separated me-scattering and photoluminescence settings. The new photoluminescence mean free path parameter here allows us to modify the color temperature of the LED output. And this is because this mean free path controls how often photoluminescence events occur. So if I reduce the mean free path, for example, to 0.05, this means that we will see more photoluminescence events, and so we should see more of a yellow result here in the shaded model. Let me run another ray trace now so we can see the results. Now you can clearly see here in the shaded model, the detector color looks a lot more yellow because we have more rays which are undergoing photoluminescence. We can also open up a new flux versus wavelength analysis with the new ZRD file that we created to show the change in flux and lumens versus wavelength. And you can see now a higher flux in lumens for this range of wavelength. Going back to the phosphors and fluorescence settings in my non-sequential component editor, I can also change the particle density here in my me scattering sections. And this will control the scattering of the unconverted blue light. Okay. And this would be important for white LED manufacturing, for example, in order to increase the uniformity of the white output and reduce the color over angle effects. So to demonstrate this, let me change the mean free path for the photoluminescence back to 0.1, so we have more of a white result on the detector here. And I'm also going to insert in a new detector. We'll do a detector polar, so we can capture more of the angular data as well. I need to change the detector color from being absorbing so that the rays pass through to the detector polar. And I'll reduce the maximum angle to plus and minus 90 degrees. Okay, now you can see the resulting detector polar, capturing a lot of those higher angle rays. I will run another ray trace. Now let's open up a detector viewer and let's view the results on the new detector polar. In the middle, we can see a color distribution that looks more white because we're combining the yellow rays which have undergone photoluminescence with the unscattered blue rays which started from our source file. Then at the edges, we see more of the yellow rays which did undergo photoluminescence. I'm going to clone this window here and lock the original. So then we can view the new results on this other detector after we change some of the other photoluminescence properties here. Okay. We're going to change the me scattering settings and we can change this particle density. If we increase the particle density or reduce the mean free path, then we increase the probability that the rays will scatter instead of photoluminesce. So let's try increasing this particle density here. And I'll run another ray trace, and then we can review the results on the polar detector. Now that the ray trace is complete, I'll exit out of this. So for reference, here was the detector viewer that we were starting with, and here's what we have now. Flipping back and forth, you can see that we see less of the yellow rays representing the photoluminescent interactions. Now we're going to show you the new auto update setting for layout windows.
Within OpticStudio, users have the ability to see all open analysis windows automatically update whenever changes are made inside of the lens data editor. That can be done by selecting the All Windows option inside of the Auto Update Mode control. However, users may have open analyses which are long running or computationally expensive, for which this control can be prohibitive. In those cases, it may still be useful for users to be able to see how their system layout is changing as they're modifying parameters inside of the lens data editor without having to have other analyses update as a consequence. To that effect, we have now added within OpticStudio 15 a new control in which users can select to update the layout windows only. In this control, as values are changed inside of the lens data editor, you'll see that the layouts themselves will be updated to reflect those changes, but all other open analyses will stay fixed and unchanged until those analyses are manually updated by hand. This control allows users to see how their layouts would be affected by changes made in the lens data editor to the geometry of the optical system without having to worry about running other analyses as a result.
Next, we're going to show you a tool that you can use to convert between coordinate break surfaces and the tilt and decenter settings in your surface properties. OpticStudio 16.5 has a new tool which allows users to easily convert back and forth between coordinate break surfaces and the tilt and decenter section of the surface properties. Let's say, for example, that I wanted to combine the coordinate break at surface 3 and the coordinate break at surface 5 into the tilt and decenter section of the surface 4 properties. In order to do this, all I need to do is select the range of surfaces and then use the new Convert Tilt Decenter to and from Coordinate Breaks feature in the toolbar of the Lens Data Editor. My first surface is surface 3, and my last surface is surface 5. And the mode we want here is to convert coordinate breaks into tilts and decenters. Click on OK. Now my mirror surface is still there, but surfaces 3, the preceding surface, and the old surface 5 are no longer there because the coordinate break information was added into the tilt and decenter section of my mirror surface properties. If you update the layout, you'll see it looks exactly the same. These representations are identical, the notation is just different. It's also very easy to go back. All I need to do is select the surface with the tilt and decenter properties and use the tool again. This time I'm going to use the mode in the opposite direction and go from tilts and decenters into coordinate breaks. And I have my coordinate breaks back. One thing to keep in mind is that you can't use pickups in the surface properties like you can for the parameters of a coordinate break. So let's say, for example, I have a pickup solve on surface 5, and it's going to pick up from the value in the same column of surface 3. If I go to convert these coordinate breaks into surface properties, the pickup solves will be removed, although the values will still be copied correctly into the surface properties. In order for this conversion tool to work correctly, the coordinate breaks before and after your surface need to be co-located. The default behavior of co-located coordinate breaks and surfaces is to apply the coordinate break value to the following surface. If you had a co-located surface that was before the coordinate break, then you could apply the coordinate break tilts and decenters into the after surface section of the preceding surface. In this example, I can't do this because there's a -50 thickness between surface 5 and surface 6. If I instead change this value here to 0, now my two surfaces are co-located, and so I could choose to put this coordinate break either on surface 5 in the after surface section or on surface 7 in the before surface section. So let's say I wanted to move the surface 6 tilt onto the after surface section of surface 5. Again, all I need to do is select the range of surfaces, then go into my new Convert Tilt and Decenters to and from Coordinate Breaks tool, and change the mode to Coordinate Breaks to Tilts and Decenters. And now I need to check the Prefer Before checkbox. Click OK. And now my coordinate break was moved onto the preceding surface and it was added into the after surface section of the surface properties. Next, we have some new operands which can be evaluated at the clear semi-diameter.
With OpticStudio 16, we introduced the ability for users to define a mechanical semi-diameter that can be different from the clear or optical semi-diameter of a surface, as shown here for surface 2. This allows users to define flats or edges to the lens that are beyond the area of ray tracing in the sequential system. With this change, we also updated all of our diameter-based operands in the merit function editor to read directly the value of the mechanical semi-diameter rather than reading the value of the clear semi-diameter. In order to provide better support for users who are going between versions of OpticStudio, i.e. to versions of OpticStudio prior to introduction of mechanical semi-diameters, as well as to give users the flexibility to be able to read either the clear or the mechanical semi-diameter in the merit function, we've now introduced a new flag for all of the diameter-based operands in the merit function editor that will allow the user to select whether they want to read from the clear semi-diameter or the mechanical semi-diameter. So for example, if we look at our merit function editor and look at the operand DMVA, which allows us to select the diameter value on a particular surface. If we look at that value on surface 2, under mode 0, we will continue the behavior that we introduced with OpticStudio 16, which is to read the value from the mechanical semi-diameter. Since this operand reports the full diameter, this is then 2 times the value shown here for the mechanical semi-diameter. If the user then wants to get the full diameter just from the clear semi-diameter value, they can then set the mode flag equal to 1 and re-update the merit function editor, and you'll see this value change. As I mentioned, this mode flag is now available in OpticStudio 16.5 for all diameter-based operands in the merit function editor.
The next feature that we're going to show you is an interactive API extension. OpticStudio 16.5 will introduce a new interactive API extension. This new feature will allow an interactive API extension to connect to an already running instance of OpticStudio. It will be very useful when attempting to control OpticStudio from a scripting environment like MATLAB or Python. This means that we can easily see how our commands affect a currently open OpticStudio file. Let me show you an example of this now. So I'll start by opening up an interactive MATLAB extension. So I just need to go to the Programming tab and expand the MATLAB drop-down menu and click on Interactive Extension. This will automatically create a new MATLAB ZOS Connection 1 folder in my user data folder, and it will open up a MATLAB script. Let me do a split screen now so you can see how this works. So now that I have MATLAB open, I just need to open up my interactive extension feature inside of OpticStudio. This is in the Programming tab and in the API section, right here, Interactive Extension. Okay. Now that I've clicked on this, it's currently waiting for the connection from MATLAB. So all I need to do now is run the pre-populated MATLAB script. Okay, and you can see the interactive extension window here is updated to say that it has been connected. Now I can type in different commands in MATLAB here to see how it affects my OpticStudio file over here. So let me start by getting this set up. I need to set the application equal to ants. Okay, and now I can start typing in some commands. So now let's try adding in a surface into my lens data editor. Okay. As soon as I hit enter, now you can see I have a new surface in my lens data editor. Okay, it's very easy. So once I'm done testing out my different commands, I can close out this interactive extension by clicking the terminate button here, or I can actually close it out from MATLAB. all I need to do is type in the application.close application, and that's it. This new interactive extension feature also allows you to specify which instance of OpticStudio you'd like to connect to. As you know, you can have two different instances of OpticStudio open. So let me open up another one and I'll show you how to do this. Okay, my OpticStudio defaults to opening the double Gauss file, but let me just open up a brand new file with a blank editor. Okay. So you can see that this is labeled as instance number 2. Okay. So if I want to connect to this instance of OpticStudio, I still need to open up my interactive extension from the programming tab. Okay. This says it's instance number 2. And all I need to do here now in MATLAB is call this script, okay, and reference it to instance number 2. Okay, here it's MATLAB ZOS connection 1, and then I want to connect to instance 2, and there you go. Now I could do the same thing, so I need to set it up. So I'm going to set the application equal to ants. Okay, and now I can add another row into my lens data editor. Okay, so I'm just going to add a surface into the lens data editor and hit enter. All right, there we go. Okay. And once I'm done, again, I can terminate the connection through MATLAB or by pressing the terminate button here. So this time I'll press the terminate button here. Okay, and that's it. Now we're going to show you how to use the new two-step Softkey transfer process. OpticStudio 16.5 will introduce a new and easier way to transfer soft keys between different computers. In previous releases, the transfer process for moving soft keys to different computers required 3 steps, and this required you to plan ahead of time in order to transfer a license. Here you can see the older interface of the Zemax License Manager with the 3 different steps that were needed to complete the transfer. In the new release, you'll notice that there is no longer a transfer tab in the Zemax License Manager. Okay. This is because now the transfer process only takes 2 steps. You transfer it away from the current machine and then onto a new machine. So all you would have to do is click on the Transfer Away button here and type in an email address to which the transfer code will be sent. Here you can see a new notification showing that my key was successfully transferred away from the current computer. So I could copy the transfer code here, but this is also being emailed here to my email address. So then all I'll need to do is take this transfer code and I can paste it into this new key section. You can see I just received the email here. And then click Apply License, and that's it. All of the feedback that you provide on the 16.5 betas will help us identify issues and fix them before the final release. Please note that these versions you're test driving are beta versions, and therefore they may contain bugs or may not function as well as the full release. If you have any questions about these betas or see something that you think is a bug, please report it to the beta release section of the Zemax forum. Also, documentation for the new features may not be complete, so the help files, knowledge base articles, and tutorials may not be updated to include the latest changes. Lastly, we recommend that you install the beta version into a separate folder in your program files so that you can run this in addition to the current release. And we've reached the summary slide. So to sign up for the 16.5 beta program, please follow the link shown here. All you need to do is enter in your name and your email, and we'll send you a link to test drive the latest 16.5 beta. We'd really like you to post your feedback and any questions that you may have on our Zemax user forum. All you need to do is go to the beta release section of the forum, then find the child forum for the feature that you're testing, and let us know what you think, or like I said, if you have a question. We'll look forward to hearing from you, and we will try to get back to you as soon as we can. Thank you very much for attending this webinar. If you have any questions about the beta program or about some of the new features that you'll be testing, you can submit them now using the questions section of your GoToWebinar control panel. If we don't have time to answer all of the questions that are submitted now, you are more than welcome to email us after the webinar at feedback@zemax.com.